Swayamprabha. Digital India. Educated India.
It is my pleasure to welcome you again to this course on CFD. Last class we started discussing about matrix inversion procedure. We listed 3 direct inversion procedure: Gauss elimination, TDMA and LU decomposition. Last class we did in detail Gauss elimination, and today's class we will see in particular tridiagonal matrix algorithm, otherwise TDMA. We know in Gauss elimination there are 2 steps: forward elimination and backward substitution. Bulk of the time consumed in forward elimination, because in the backward substitution it becomes completely upper triangular and we start from the last row and substitute and get the unknown. Hence, most of the time is appeared to be spent in the forward elimination process. We also learned different discretization procedure, for example, central differencing, forward differencing, backward differencing, pure upwinding, quick and combination. And whatever the method you follow, for some combination the coefficient matrix will result in what is known as a tridiagonal form. And we have already seen in previous class diagonal matrix, tridiagonal matrix and pentadiagonal matrix. The tridiagonal matrix structure is displayed here again. So, this will have one main diagonal which is marked here in red color, and immediately above is a super diagonal and immediately below is a subdiagonal. So, you see in this matrix we have values restricted only to limited region of the matrix, and you have for most of the places zeros. So, obviously matrix of this nature applying Gauss elimination is not economical. So, we need to find some alternative way where you do not need to handle zeros, hence reduce computational time substantially. So, we follow what is known as a simplified form of Gauss elimination procedure. It was proposed by Thomas, which is called Thomas algorithm for tridiagonal matrix. In short form it is called TDMA. Only one element needs to be eliminated in the forward elimination process. Then when the algorithm reaches the last row, you have an equation with only one unknown on the left side and known on the right side. So, you are immediately able to get the unknown. Then we follow what is known as a backward substitution to get all the unknowns. We will see TDMA little more detail now. So, when ordinary differential equations or partial differential equation or finite difference, say in this case central differential scheme, we know in central differential scheme we have node of interest and one node on either side, left as well as right, and if you apply CDS scheme for the full domain, then the resulting algebraic equation will have a simple structure, and each equation will have variables at its own node and immediate left as well as right. Such a system, linear equations with n rows is given here. So, B1 U1 plus C1 U2 equal to D1, and you go to the next row A2 U1 plus B2 U2 plus C2 U3 equal to D2, and all the way up to the nth row AN UN minus 1 plus BN UN equal to DN. Now, in the first row you have only 2 contribution, that is because you have a on the left side boundary condition, and boundary condition is accounted as a source term and that is added and you get D1. Similarly, the last row again has only 2 contribution. The for the last row, the right side is again boundary condition, and that is appearing as a source term and added to known value d n. Now, the same algebraic equation in the form of matrix, it is shown here. So, B 1 C 1 remaining all zeros. Similarly, all the way up to the last row A and B n, this is a coefficient matrix multiplying the unknown column vector u 1 to u n on both on left side, then on the right side you have a known column vector. We repeat that again here, and to solve this we follow the same procedure as Gauss elimination procedure, that is you have a forward elimination and backward substitution. Only thing, it is slightly modified for this matrix structure, and after working out you are able to set what is known as a recursive relationship, and that is what is shown here. So, u n, which is the last unknown, is equated to q n, and you go in the reverse because now it is a backward substitution, u I equal to q I minus u I C I by P I, where I goes from n minus 1 in the reverse order all the way to 1. So, this is what is a backward substitution. Now, we define q and p as given here, p 1 is equal to b 1, q 1 is equal to d 1 by p 1, and then this is for the first. For the remaining from 2 to n, q and p are defined as shown here. Now, this relationship is already worked out. What I am showing here is a only final expression, and this is in the form of a recursive relationship. What is shown here is a sample Fortran code listing to achieve what is known as a TDMA. So, equations are numbered from 1 to n. One special point to be noted here is matrix has values only along 3 diagonals: main diagonal, subdiagonal and super diagonal. Remaining elements are all 0. So, we do not store the matrix in full form, we only store main diagonal, super diagonal and subdiagonal as independent matrix, and that is what is A, B and C. So, in A, for example, we will have all elements belonging to the subdiagonal, B will have elements belonging to the main diagonal, and C will have elements belonging to super diagonal. So, they are independently stored. That way you do not store a full matrix, because the full matrix has zeros and it is expensive in terms of memory as well as handling those zeros, and that is the speciality of this TDMA procedure. And we also notice we have one more column vector on the right side, known column vector, and that is stored in D, and X is the unknown column vector. So, we call subroutine TDMA with arguments, and you define A, B, C, D, and we define new 2 new variables P and Q related to the recursive relationship. So, we follow the formula and write this Fortran listing. This will result in some form of forward elimination. And the next step is a backward substitution. There you get solution vector itself. So, the last row is the one that we find first. So, x of n is equal to q of n, then we do in the reverse n 1 to n 1 equal to n minus I, we go in the reverse and you find complete column vector. We also have a similar sample code listing, but written in C language as shown here. So, double star A star B star C, as we did before, A, B, C are diagonals corresponding to main diagonal, subdiagonal and super diagonal, and n is the number of rows that is required to be solved. Then you modify. So, in this, instead of P and Q in the previous slide, here we define some other quantity, you calculate D, then you substitute in the backward substitution form, you get answer for unknown column vector. We will try to take an example problem and explain TDMA procedure. Problem statement: solve one dimensional diffusion equation in the domain x going from 0 to 1 with the boundary condition u x equal to 0 comma t is always 0 and u 1 comma t equal to 0 for all time greater than or equal to 0, and at initial condition that time is equal to 0 we have boundary condition u x comma 0 equal to sin phi x. So, this is the initial condition and these are all boundary condition applied at x is equal to 0, at x is equal to 1 for t greater than or equal to 0, and specifically it is given follow Crank-Nicolson scheme, CN scheme. We already learned this before, we will repeat it here again. So, consider one dimensional unsteady diffusion equation dou u by dou t minus alpha dou squared u by dou x squared equal to 0. We know what is FTCS, that is forward in time, central in space. So, we have forward in time for time derivative and central in space for second order spatial derivative. And this is a explicit scheme in the sense all the variables are known from the previous time level, that is what is given in the superscript as n. The current value to be determined is given in the superscript n plus 1, and that is the only one quantity appearing for the entire equation, remaining all from the previous time level. And in terms of schematic, that is shown here. So, n plus 1 level value required at n plus 1 level is determined from values already found at nth level. In this problem specifically it is asked Crank-Nicolson scheme. So, for the same governing equation we write down Crank-Nicolson scheme and that is shown here. So, at the left hand side you have the time derivative term that is same forward in time. The difference is only for the spatial dou squared u by dou x squared, that is written in the form of Crank-Nicolson scheme. We know Crank-Nicolson scheme is a semi implicit scheme, that is it is half explicit and half implicit, and you are able to identify that here. So, we have one set of term with superscript n plus 1, we have another set of term with a superscript n, and there is a weightage of half, that is what is in the denominator here too. Corresponding molecule is schematics is given here. So, n plus 1 value is determined with the values from n plus 1 as well as values known from nth level. Now, we can rewrite this specifically for the sake of writing code. R is a new variable defined as alpha delta t by delta x squared, and all these n plus 1 values are to be determined. So, we take all of them onto the left hand side and all quantity with a superscript n is known from the previous time level and they are taken to the right hand side. This equation needs to be solved when you apply Crank-Nicolson scheme. Now, if you put this in the form of a matrix. So, in this last slide for the example problem one dimensional diffusion equation, we define discretized equation. Now, we define computational domain as shown here. It is going from x is equal to 0 on the left side to x is equal to 1 on the right side. We take 4 spacing, otherwise 3 grid points. So, at 1, 2 and 3, and they are equally spaced on delta x happens to be 0.25. On the left side boundary condition is defined as well as on the right side boundary condition is defined. Now, for the sake of simplicity we assume delta t and alpha in such a way value r equal to 1, and we already define r to be alpha delta t by delta x squared. We rewrite the discretized equation here again. Now, we use the value r and apply the discretized equation at every nodal point, and we get algebraic equation as shown here. As you can observe, first row has an influence of left side boundary, last row has an influence of right side boundary. Now, the same algebraic equation is written in the form of a matrix as shown here, that is 4 minus 1 0 minus 1 4 minus 1 0 minus 1 4, a coefficient matrix, and then one unknown column vector, on the right side you have a known column vector. Now, we apply the recursive relationship, we define two quantities P and Q. So, P 1 Q 1 and P I Q I for I going from 2 to n, they were also defined. We try to apply this for this example problem. So, we get P 1 equal to B 1 equal to 4, Q 1 is equal to 0.25, and we calculate other values, for example, P 2 Q 2, P 3 Q 3. Once you find this, then we do the backward substitution, and that is also defined in terms of recursive relationship. U n is equal to Q n and U I is equal to Q I C I U I plus 1 P I, and it is backward substitution. So, I is going from n minus 1 all the way to 1. We substitute n is equal to 3, that is the last row, and then n minus 1 is equal to 2. So, we get U n equal to Q n, which is otherwise U 3 equal to Q 3 equal to minus 1, and we calculate for the remaining U 2 U 1 using this relationship and substituting appropriate values, and values are shown here. So, it is so easy in TDMA. Now, we have the TDMA for a simple system, but in some problem you may have to force what is known as a periodic boundary condition. Periodic boundary condition means values are repeated from one boundary to the next boundary, and the domain is supposed to extend in the periodic way indefinitely. When such situation is there, we pose periodic boundary condition. The matrix, the TDMA, the tridiagonal matrix gets slightly modified as shown here. So, the main diagonal, subdiagonal, super diagonal, they are same. Now, in the first row we have one more element or value added in the last column as shown here A 1. Similarly, last value in the first column again gets altered by the periodic boundary condition, and it is shown here as C n. The TDMA procedure which just now explained is suitable for other boundary condition, and it is slightly modified as Sherman Morrison formula. We are not going to discuss that here, and still we can use the TDMA procedure we have explained. So, overall, as you observed through example problem and also through recursive relationship, we understand it is very easy to program, and in practice you do not actually have full coefficient matrix stored, only diagonals are stored as a separate column vector. Number of operation, because we are not handling with the zeros, number of operation when compared to the Gauss elimination procedure is substantially reduced. Now, it is only of order n. It saves lot of computational time because we are not handling zeros, and memory requirement is also less. It is one of the successful algorithm, and it is used by many researchers for their own calculation. Cases where you end up getting pentadiagonal matrix, for example, we learned before what is known as the alternating direction implicit. Alternating direction implicit was a reduced form of the pentadiagonal matrix solution procedure, where the original pentadiagonal matrix is reduced into two tridiagonal matrix by having a method of explicit in x direction, implicit in y direction, and the next stage implicit in x direction, explicit in y direction. We learned that before, we will see that again. So, by that procedure the original pentadiagonal matrix gets reduced to tridiagonal matrix. Similarly, there is another operation called operator splitting that also results in reducing original matrix into tridiagonal matrix. There are procedures available to convert pentadiagonal matrix and septadiagonal matrix into tridiagonal matrix. Once it is reduced, then we can apply TDMA procedure to get the solution. We have listed three direct methods. One is a Gauss elimination, second is a TDMA, third one is a LU decomposition. In LU decomposition, the full matrix A is split or decomposed into 2 as A is equal to L into U, where L stands for lower triangle matrix and U stands for upper triangle matrix, and that is in the form of matrix structure is shown. A full original coefficient matrix is decomposed into L matrix and U matrix. So, in this class we have seen in detail triangle matrix algorithm procedure. We also had an example problem. We listed advantages associated with the TDMA procedure, and in the next class we are going to see details about what is known as a LU decomposition, again with the listing and example problem. Thank you.